It's February 14th, 2026. If you're listening to this, you've likely spent the last 12 months just watching the global supply chain fracture in real time.
Yeah.
We used to talk about supply chains as these invisible, almost boring logistical rivers that just worked, you know?
Hmm.
You order a phone, it arrives, you build a fighter jet, the parts show up.
They just appear.
Exactly. But the last year, and I'm talking specifically about the escalation throughout 2025, has completely shattered that illusion. We are looking at the end product of a very long, very invisible war over 17 specific chemical elements.
Rare earth elements, the REEs. And you're right, the boring days are officially over. I think
Yeah.
we're living through what historians are almost certainly going to call the defining year of the resource war.
It really feels like the ground shifted under our feet. We went from these vague concerns about dependency to full-blown trade wars, export bans, and what looks like a desperate scramble for national
The
security.
scramble.
But the mission for this deep dive isn't just to recap the scary headlines. We want to understand the mechanics of this crisis. Because when the world's superpower in refining China decides to, turn off the tap, it doesn't just mean prices go up. It forces a fundamental rethinking of physics and engineering.
That's the angle that gets missed so often. This isn't just about digging more holes in the ground somewhere else. It's about how we design the machines that run the entire modern world. We're going to look at how engineers are redesigning the electric motor from the ground up, effectively hacking their way out of a geopolitical corner.
And we have a massive stack of sources today to help us navigate this. We've got the latest audits from the Department of Defense, deep technical analysis from ID TechX, reports from the USGS on strategic reserves, and some pretty dense engineering journals regarding motor topology.
Yeah, some heavy reading.
So let's start with the stakes. Why are these 17 elements the invisible backbone of modernity?
Well, to answer that, you really have to look at the intersection of high technology and high performance. The modern world, whether it's the EV in your driveway or the guided missile in a silo, it runs on magnets.
Right, magnets.
But not just any magnets. We are talking about high-performance permanent magnets, specifically things called neodymium iron boron, or NFeB.
The super strong ones.
The super strong ones, exactly. And another type called samarium cobalt, or SEMCO.
And the scary part isn't just that we use them, it's how much we rely on them. I was reading that DoD report you sent over, and the dependency numbers are just stark. They estimate that something like 78% of U.S. weapons programs contain components dependent on rare earth magnets.
78%.
That's almost 8 out of 10 systems.
It is a staggering vulnerability.
Yeah.
And it's not just nice to have tech, it's mission critical. If you look at the F-5 Lightning IIs, which is, it's the cornerstone of NATO air superiority.
The poster child for this whole problem.
It really is. It is effectively a flying brick of rare earth elements. A single aircraft requires over 900 pounds. That's roughly 418 kilograms of these materials.
Okay, let's drill down on that. 900 pounds is a massive amount of material for a fighter jet where every single ounce is supposed to count. Where is it all going?
It's distributed all throughout the airframe. The biggest consumers by far are the electric actuators.
Okay.
In previous generations of aircraft, you used hydraulic systems, heavy pipes, pressurized fluid, to move the flaps, the rudder, the ailerons.
The old way.
The old way. The F-35 uses what are called power-by-wire. It uses high-power electric motors to move those control surfaces. And to get the kind of torque required to move a wing flap while you're flying at supersonic speeds, you need magnets with an incredibly high flux density.
So you're trading hydraulic weight and complexity for magnetic density.
Exactly. And then you have the radar systems. The AZR radar uses rare earths in its transmitter receive modules, the jamming pods, they require them, and the engine turbo machinery itself. It relies on them for sensors and comps.
This brings up a really critical distinction in the physics of these materials then. We have neodymium, which everyone knows as the standard supermagnet, and then you mentioned samarium cobalt. Why do we need both? Why not just stick with neodymium, the strongest one?
This is where the thermal stress analysis comes into play, and it's frankly why the defense sector is so panicked. Neodymium magnets, the NdFeB ones, are the strongest commercially available magnets at room temperature. They are fantastic.
At room temp.
At room temp. But they have a major, major weakness, heat. If you heat a standard neodymium magnet, it suffers from what we call thermal demagnetization.
It loses its grip. It gets weaker.
It does. And there are two stages to this. There's a reversible loss where it gets weaker, but then it comes back when it cools down. But if you hit what's called the Curie temperature, or even just the maximum operating temp before that, the magnetic domains inside scramble permanently. The magnet dies.
It's just a lump of metal at that point. It's a paperweight. Now think about the inside of a jet engine or an actuator on a missile fin that's traveling at Mach 3, just dealing with air friction. It gets incredibly hot.
So neodymium is just, it's out. It's not an option for those applications.
Precisely. That is where samarium cobalt, SEMCO, steps in. It has a slightly lower maximum energy product, so it's a little bit weaker than neodymium at room temperature, but it is thermally stable up to about 350 degrees Celsius, sometimes even higher depending on the grade.
Okay, so for the critical, really hot sections of the F-35 or a missile turbine,
Yeah.
you must use samarium cobalt. There's no alternative.
You must. And that specific material was the cause of a major supply chain scare not too long ago, wasn't it?
The pump incident, yeah, I remember this. Deliveries of the F-35 were actually halted for a while because auditors found a Chinese-made samarium cobalt alloy in a turbomachine pump.
And the Pentagon didn't even know it was there.
Yeah.
That's the crazy part. It was buried, tiers and tiers down in the supply chain. It just highlights the opacity of the entire system. You think you're buying an American pump from an American supplier, but the tiny magnet inside the motor, inside that pump, came from a refinery in Jiangxi.
Exactly. And the scale of this problem, it goes way beyond just aviation. Look at naval power. A single Virginia-class submarine requires roughly 9,200 pounds of rare earth materials.
9,000. Wait. 9,200 pounds. That's over 4 tons.
4 tons per sub.
I assume most of that is for the electric drive system, for stealth.
It is. Stealth is life for a submarine. Traditional mechanical drives with gears, they make noise. Vibration is death.
Right.
Large permanent magnet motors allow for a direct drive propulsion system. It's incredibly smooth, it's silent, and it's unbelievably power dense. If you want to run silent, you are completely dependent on these magnets.
And it's not just the propulsion, is it?
No. Plus the sonar transducers, the very ears of the boat. They use something called terphenol D, which is an alloy of terbium, dysprosium, and iron. It literally changes shape when you expose it to a magnetic field, and that's how it creates the sound waves for the sonar ping.
And then there's the volume problem with munitions. A JDAM guided bomb or a Tomahawk missile, they use a relatively small amount per unit, maybe a pound or less for the little guidance fins. But we don't buy 5 missiles, we buy thousands.
Right. The aggregate vulnerability is massive. It's a death by 1,000 cuts problem. If you can't steer the bomb, it's just a dumb bomb. It's useless. And those guidance fins rely on miniature high-torque motors to adjust the flight path second by second. No magnets, no precision guidance.
So the military reality check is grim. We are, for all intents and purposes, chemically dependent on arrival power for the basic functionality of our most advanced defense systems. And that brings us to the defining year, 2025. This wasn't just a year of realizing the problem, it was the year the trap finally snapped shut.
It really was a masterclass in economic statecraft or, economic warfare, depending on your perspective. It started pretty quietly in April 2025 with restrictions on 7 specific heavy rare earths. But the real escalation, the big one, happened in October 2025 with the 0.1% rule.
I remember reading about this and thinking it just sounded like some bureaucratic footnote, but it's actually a poison pill for the entire global supply chain. Can you unpack the 0.1% rule for us?
Yeah, it's deviously clever.
Yeah.
Essentially, China expanded its export control list to include downstream products, not just the raw materials. The regulation states that foreign firms need specific approval to export magnets containing even trace amounts, 0.1% of Chinese origin heavy rare earths.
So heavier rare earths like dysprosium or terbium.
Exactly, those two.
So let me get this straight. If I'm a magnet manufacturer in, say, Japan, and I buy a tiny pinch of dysprosium from China to stabilize my high-temperature magnets, suddenly I can't sell that magnet to a U.S. defense contractor without asking Beijing for permission first.
That is the mechanism, precisely. It creates extraterritorial control over your business. It forces the manufacturer to make a choice. Do you segregate your entire supply chain, which is incredibly expensive and technically very difficult? Or do you comply with the licensing and essentially give China direct oversight of your customer list?
It's a loyalty test.
It is. And then came December 2025, the nuclear option.
Right.
This was the explicit denial of export licenses to any companies affiliated with foreign militaries. That was the line in the sand. It was a clear, unambiguous signal. We will not supply the materials for your weapon systems anymore.
We keep mentioning dysprosium and terbium. You called them the vitamins of the magnet world in our pre-show notes, which I thought was a great analogy. Why are these specific elements the choke point? I mean, we mine rare earths in California, don't we?
We do, yeah. MP Materials in Mountain Pass mines plenty of neodymium and praseodymium, but those are what we call light rare earths. Dysprosium or di and terbium, TB, are heavy rare earths.
And they're different geologically.
Very different. Their distribution is different, and they are much, much harder to separate. They are the additives you mix into a neodymium magnet in very small amounts to increase its coercivity.
It's resistance to heat.
It's resistance to demagnetization at high temperatures, yes.
Yeah.
So if you want an EV motor that doesn't fail when you're climbing a long hill, or a fighter jet radar that doesn't conk out when it heats up, you need the heavies.
You absolutely have to have them.
You absolutely do. And currently, China controls roughly 99% of the world's refining capacity for these specific heavy elements. That is the bottleneck. It's not
Yeah.
the mining, it's the refining. You can have all the neodymium in the world, but without that dysprosium vitamin, it's useless for almost any high-performance application.
So, given all that, how is the U.S. responding? We're hearing about the expanded USGS critical minerals list and this thing called Project Vault. Is this just the old National Defense Stockpile with a new, fancier marketing name?
It's fundamentally different, and that's a really important distinction to make. The old stockpile was basically the government buying rocks and sitting on them for decades.
Right.
Project Vault, which was formalized recently, is a $12 billion strategic mechanism, and it's a public-private partnership. $10 billion comes from an Export-Import Bank, or XEM, loan, and a crucial $2 billion is meant to come from private capital.
So, how does it work in practice?
It's OEM-driven. It's really a piece of financial engineering designed to support material engineering. So manufacturers think Ford, General Dynamics, Lockheed, they pay what's called a commitment fee, which is almost like an insurance premium, to book capacity in this reserve.
Okay, and in return,
In return, the reserve guarantees a price floor for any new domestic mines.
why is the price floor so critical?
Because of the history of this market, every single time a Western company has tried to open a heavy rare earth mine or refinery in the last 20 years, China has flooded the market with cheap material, dropped the global price by 60 or 70%, and bankrupted the competitor.
It's predatory pricing.
Classic predatory pricing. Project Vault says, we don't care what the global price is. We will buy from our domestic partners at this minimum price no matter what. It de-risks the massive capital investment required to build these facilities in the U.S. or Australia or Canada.
So it effectively neutralizes the primary economic weapon of price manipulation.
That's the goal, exactly. And it ties into another initiative called FORGE, the Forum on Resource Geostrategic Engagement. This is basically an attempt to create a preferential trade bloc, a club of 54 nations all agreeing to harmonized standards for this stuff.
A parallel supply chain.
A parallel supply chain. If you are in the Forge block, you get access to the Project Vault mechanism. It's an attempt to build a closed-loop economy that, well, that excludes the adversary.
So that's the political and financial counteroffensive. Dig more, refine more, stockpile more. But there's a much more fascinating counteroffensive happening in the engineering labs, the technological counteroffensive.
This is where the story really pivots from, despair to innovation. Because if you can't secure the supply, you eliminate the demand. We are seeing a massive shift in motor topology. In 2022, something like 82% of EVs used rare earth motors.
The vast majority.
Yeah. By 2030, that number is projected to drop to 70% or even lower, specifically because engineers are figuring out how to make powerful, efficient motors without any magnets at all.
Let's break down the contenders then. The leader of the pack, it seems to be the externally excited synchronous motor, or ESM. I know BMW and Renault are betting the farm on this. How does it work?
Okay, so in a traditional permanent magnet motor, the rotor, the spinning part inside, has these powerful rare earth magnets literally glued to it. Those magnets provide the magnetic field for free, essentially.
They're always on.
They're always on. In an ESM, you take the magnets out. You just remove them. And instead, you put copper windings on the rotor. When you want a magnetic field, you inject electricity into those copper coils. You create a powerful electromagnet on the fly exactly when you need it.
But isn't there a penalty for that? I mean, if I have to use my precious battery power to both energize the rotor and spin the car's wheels, aren't I just losing efficiency compared to a magnet that is always on for free?
That's the intuitive conclusion. And at very low speeds, yes, there is a slight efficiency penalty. You are spending a little bit of energy to create that field. But here is the big highway advantage.
No.
In a permanent magnet motor, that magnet is always on. It's always pulling and creating drag. So when you are coasting at 70 miles per hour on the highway or rolling downhill, The permanent magnets are actually creating resistance. We call it iron loss or drag loss. It's like having a very slight brake pedal applied all the time.
And with the ESM,
You just cut the current to the rotor, the magnetic field completely vanishes, the car coasts with zero magnetic drag. So at highway speeds, which is where EVs traditionally struggle with range, the EESM can actually be more efficient than the rare earth motor.
wow, that's a massive selling point. But there's a mechanical complexity issue, right? How do you get electricity onto a shaft that's spinning at thousands of RPM?
That's always been the Achilles heel. Historically, you used brushes and slip rings, physical contacts that rub against the shaft. They create carbon dust, they wear out, they need maintenance. It's very old school tech.
But I understand ZF, the big German supplier, has a solution for this.
They do. It's a game changer. They introduced what they call the I2SM, the inductive externally excited synchronous motor. It uses an inductive exciter. The easiest way to think of it is like the wireless charger for your phone, but it's installed inside the motor shaft.
So it's beaming power.
It beams the energy across a tiny air gap into the rotor coils. No brushes, no friction, no dust, no wear parts. And as a bonus, it reduces the axial length of the entire motor by 90 millimeters, which is a huge deal for packaging in a car.
That's incredible. So you get the magnet-free independence without the historical maintenance penalty.
Okay, so let's contrast that with technology B, the induction motor.
Yeah.
This is what Tesla used back in the day, right? Yes, the asynchronous or induction motor. This is the rugged, simple workhorse of the motor world. Tesla used it on the original Roadster and the early Model S. It uses what they call the squirrel cage rotor, which is literally just bars of aluminum or copper arranged in a cylinder.
No windings, no magnets.
No windings on the rotor, no magnets, no brushes. You don't inject current directly into it. You induce a current by spinning the magnetic field of the stator around it.
It sounds much simpler.
It is much, much simpler. It's structurally rugged. You can abuse it. It's cheap to make because it's just steel and aluminum, common materials. But it's heavy. For the same power output, an induction motor is generally about 30% larger and heavier than a permanent magnet motor.
And less efficient?
And less efficient. Its peak efficiency is lower, around 93% versus 97% for a good permanent magnet motor.
So it's good for, say, a backup motor in a dual motor setup or maybe a heavy truck, but it's not ideal for a high-performance sedan where you're fighting for every last mile of range.
Correct. And that's exactly how Tesla uses it now. It's often the secondary motor in their dual motor vehicles. It sits there dormant and totally drag-free until you stomp the accelerator, then it wakes up to add a huge burst of power. But it's not the primary efficiency driver.
Okay, now let's talk about physics hacking. Ferrite magnets. Ferrite is, it's basically rust, right? Iron oxide.
Essentially, yes. It's a ceramic material, it's dirt cheap, and it's incredibly abundant. The problem is it's weak. A good neodymium magnet has a field strength of roughly 1.4 Tesla. Ferrite is down around 0.4 Tesla.
So it's not even close.
Not even in the same league. It's significantly weaker.
So how in the world do you make a high-performance car with such weak magnets?
You go back to the fundamental physics equation for power. Power equals torque times speed.
P excess.
Right. If your magnets are weak, your torque is low. So to get the same power, the same P, you have to drastically, and I mean drastically, increase the speed that
You just have to spin it insanely fast.
much, much faster. We are talking 20,000 RPM or even higher.
But doesn't the rotor try to tear itself apart from centrifugal force at that speed?
It absolutely tries to. And that's why you see these incredible innovations like the motor in the Tesla Plaid, which uses a carbon fiber sleeve that's wrapped around the rotor under extreme tension. It acts like a containment suit, physically holding the magnets in place under the insane G-forces.
So you're using material science to overcome the limits of magnetism.
Exactly. And now, companies like Proterial and Hitachi Astemo are applying this high-speed concept to ferrite motors. The thinking is, if you can spin a ferrite rotor fast enough and develop the materials to keep it from exploding, you can actually bridge the performance gap with neodymium for mass-market cars.
That is just brute force engineering, and I love it. Okay, finally, the one you called the Holy Grail. Iron nitride. This sounds like pure science fiction.
It has been for a very long time. Iron Magnetics is the company that's really leading the charge on this. Iron nitride, its chemical formula is Fe, has a theoretical magnetic saturation of 2.5 Tesla.
Wait, hold on. Neodymium is 1.4 Tesla. You're saying this could be nearly double the strength?
Theoretically, yes. It has the potential to be significantly stronger than any rare earth magnet. And here's the kicker. It's made of iron and nitrogen-2, the most abundant and cheap elements on Earth.
So what's the catch?
The catch has always been manufacturing stability. It's a very difficult material to synthesize in a stable bulk form. But Nairn is now partnering with major players like Stellantis and some big Indian OEMs to try and scale this up. If they succeed, it just renders the entire geopolitical chokehold completely irrelevant because we would get better performance from common materials.
It changes the entire game board, so the technology exists, or at least it's emerging. But the adoption seems really uneven. Let's move to segment 4 and look at the regional strategies. It seems like the EU, India, and the US are playing three completely different games here.
No. They really are. The European Union is acting as the regulator.
Yeah.
They passed the Critical Raw Materials Act, the CRMA, which sets these very hard, ambitious targets: 10% domestic extraction, 40% domestic processing, and 25% recycling by 2030.
But there's a problem, right?
There's a big problem. Europe has very few rare earth mines and has some of the strictest environmental laws in the world. Digging new holes in Europe is incredibly slow and expensive.
So the regulation is way ahead of the geological and political reality.
Yes, exactly. And that is precisely why the European OEMs, BMW, Renault, and suppliers like ZF are the undisputed global leaders in magnet-free tech. They looked at the situation and realized they cannot rely on domestic mining to save them in time, so they're engineering their way out of the problem.
They're building a technological insulation layer.
They are. They're essentially immunizing themselves against the export bans through pure innovation.
And for this to work, what kind of regulatory instruments do analysts recommend Europe put in place to complement this tech lead?
The big recommendations are for things like material passporting. So an EV sold in the EU would need to declare the origin and composition of its motor materials. And then you could tie that to incentives, right? Give tax breaks or subsidies for vehicles with non-RE drivetrains. It creates a market pull for the very technology their companies are perfecting.
Okay, and what about India? You called them the leapfrogger.
India is in a really fascinating position. They have a massive, rapidly growing auto market, but they lack the legacy supply chains of the West. They don't have a huge sunk cost in rare earth refining infrastructure. So you have companies like Sterling G-Take and Simple Energy that are just moving straight to magnet-free motor architectures.
It's like how some developing nations skipped landline phones and went straight to a cellular network.
It is the perfect analogy. They are leapfrogging the problem.
Yeah.
You have startups like Chara Technologies that are scaling up rare earth-free reluctance motors. That's another magnet-free design that are scalable and cheap. They are turning their lack of processing infrastructure into a strategic incentive to innovate faster. They are actually targeting commercial production of these motors before the 2030 deadlines the West is struggling to meet.
And then there's the United States, the stockpiler.
Yes, the U.S. strategy is heavily focused on reshoring. The Inflation Reduction Act, the Defense Production Act, Project Vault, it's all about throwing massive amounts of capital at the problem to rebuild the domestic supply chain. We want to dig the holes and refine the ore here.
But you mentioned there's a critical metric that U.S. policy analysts need to be watching like a hawk. It's not just about mining, is it?
It's not. That is the key ratio that everyone needs to track, the ratio of domestic mining to domestic refining. For years, we mined rare earth at Mountain Pass in California, put the raw concentrate on a boat, and sent it to China for the complex chemical separation.
We were essentially a resource colony for their high-tech industry.
We were. So the ultimate success of the U.S. strategy depends entirely on the new refining capacity coming online in places like Texas and California. If we just dig it up but still can't separate the dysprosium from the terbium ourselves, we haven't solved the national security problem at all.
We're just moving dirt from one part of our territory to another before sending it overseas.
Precisely. We're just rearranging the deck chairs. So the key metric from any USGS-style report isn't just tons mined. It's tons of separated heavy rare earth oxides produced domestically. That's the number that matters.
Okay, let's pivot to the final piece of this puzzle, which often gets overlooked. Segment 5, the environmental ledger. Because so often, green tech has a very dirty backstory.
It's the great green paradox, isn't it? We are, in some cases, tearing up the earth to save the climate, and rare earth mining is notoriously dirty. To get these elements out of the rock, you often have to use a process called heap leaching with ammonium sulfate.
Give us a sense of the scale of the waste from that process.
The numbers are mind-boggling. According to multiple sources, extracting just 1 ton of rare earth elements can generate up to 2,000 tons of toxic waste.
2,000 to 1?
Yes. And this includes radioactive tailings, because these elements are often found geologically alongside thorium and uranium. If you look at satellite imagery of the major mining sites in Inner Mongolia or the largely unregulated mines in Myanmar that feed China, it is just ecological devastation. We're talking acid wastewater, poisoned groundwater, entire landscapes ruined.
So when a company like BMW or Renault makes the switch to an EESM motor, it's not just a geopolitical or an economic play, it's a massive environmental win.
A massive one. A magnet-free motor reduces the total manufacturing CO2 footprint by anywhere from 30% to 50% compared to a permanent magnet motor. You are eliminating the hugely energy-intensive mining, the chemical-intensive refining, the radioactive waste management, and the global shipping of heavy metal oxides from one continent to another.
And what about end of life? We talk so much about the circular economy.
This is where magnet-free really shines. Recycling a permanent magnet motor is an absolute nightmare. The magnets are glued into the rotor slots with high-strength epoxy. To get them out, you either have to shred the entire motor, which often shatters the brittle magnets into a useless powder, or you use complex and hazardous chemical baths to dissolve the glue. It's expensive and it's dangerous.
But a copper coil motor like an EESM.
It's just steel and copper. We have been recycling steel and copper efficiently for over a century. You just chop it up, melt it down, and you make a new motor. It is fully, easily recyclable with existing global infrastructure.
So let's try to synthesize all of this. We started this deep dive with a really terrifying premise that the modern world, our jets, our cars, our phones, is essentially held hostage by a supply chain we do not control. But as we've peeled back the layers here, the story has really changed.
It has. The big aha moment for me in all of this is that the crisis itself is the catalyst for something objectively better. If rare earths had remained cheap and abundant forever, we would have just kept using them. We would have accepted the environmental damage and the huge geopolitical risk because it was the easy engineering path.
But the constraint, the war as we called it forced us to think harder.
It forced BMW to perfect the wireless rotor. It forced Tesla to use carbon fiber to contain a 20,000 RPM motor. It forced Niren to finally crack the code on iron nitride. We aren't just finding good enough substitutes. In many cases, we're finding superior engineering solutions. An ESM is better on the highway. A magnet-free motor is cleaner and easier to recycle.
So looking out to 2030 and beyond, where does this all land?
I see a bifurcated market developing. The defense sector, the F-35s, the Virginia-class subs, they will almost certainly stay with rare earths. They need the absolute maximum performance density, and cost is no object. Project Vault will exist specifically to protect that narrow, critical supply chain.
And the rest of us, the civilian world.
The mass market, the 100 million cars and trucks produced every year, will migrate away. They will go magnet-free or ferrite. They will decouple themselves from the strategic risk because it's cheaper, cleaner, and ultimately more resilient.
Which leaves me with a final, kind of ironic thought. We've spent the last decade absolutely terrified of China's monopoly on these materials. But if this magnet-free revolution really succeeds,
then China could be left holding a near-total monopoly on a strategic resource that the commercial world no longer desperately needs. They might find that their most powerful economic weapon has become obsolete because the target simply moved.
So is the ultimate solution to the rare earth war simply to stop fighting it and to change the entire battlefield?
It certainly looks that way. The best way to win the game is to stop playing.
A fascinating shift in perspective, from vulnerability to innovation. Thanks for unpacking all of this with us on the Deep Dive.
It was my pleasure. Always is.
And thank you for listening. We'll see you in the next one.